In this video, we are going to continue our discussion on Unit 3. This is lesson number 2 for part number 1. In this video, I'd like to talk a little bit more about the properties of logarithms and also introduce some word problems. We're going to be utilizing the definition of a logarithm and how it's an inverse of an exponential in order to establish a few of our properties, and these properties would be helpful for problem solving a little bit later. Now, the definition from the last lesson is shown here, and we're just implying or indicating that a logarithmic equation, when written like this, is equivalent to this equation here when written as an exponential. You'll notice that the input of the logarithm becomes the output of the exponential, and the output of the logarithm is the input of the exponential, and vice versa. We did have some restrictions, however. The a value, the base of the logarithm, and the base of the exponential must be positive, and it may not be equal to 1. And again, we're saying that not because it's impossible to do the work in that case, but it doesn't produce very reliable results. It's not something that we can traditionally count on when we deal with negative base values. We'll address that at another time. We also said that x must be positive as well. This is our way of restricting the domain. So let's take a look at this particular example here. We don't know what the base of this logarithm is, and in fact the base doesn't even matter. But we're being asked to find the logarithm base a evaluated at 1, and we've got to find out what that's equal to. Well, if we need to solve that or evaluate it, what I usually do is write equals x, because that's our unknown value. This is what we're trying to solve for. And if I can't establish the result for the logarithm by simply looking at the expression, then I'm going to rewrite this logarithm as an exponential. And part of the definition produced this loop rule that I was talking about in the last video. If you start at the base a and loop across the equal sign back to our argument here, the target value number 1, then that order or that loop right there will allow us to rewrite this logarithm as an exponential. So we know that if the logarithm base a of 1 is equal to x, then a to the x power has to equal 1. Now here again, I don't know the base value here, but it will be some number. And I'm asking myself, if I had some number raised to some power and the result had to be equal to 1, that looks kind of familiar. And I think I remember that any base to the power of 0 always equals 1. And that would be a true assumption, if you could recall that as well. Any base raised to the power of 0 will equal 1, so therefore x has to be equal to 1, and therefore we could say that a logarithm with any base value at all, as long as the a value meets our criteria before, that's positive and not equal to 1, any logarithm base a of 1 will always equal 0. So should we find ourselves in a larger problem, and we can simplify a component of that large problem into this particular phrase, well, we know that that phrase right there is exactly the same as the number 0. It's equivalent and equal to 0. Similarly, if we're being asked to find logarithm base a of the same number a, we could treat that as a logarithm equal to x, and use the loop rule to rewrite this as an exponential if you can't evaluate the logarithm on your own. So we now know that a to the x power is equal to a, and any base to some power that equals itself, some number raised to a power will equal itself, well, that power has to be 1. Any base to the power of 1 will be equal to that number itself. Therefore, again, should we encounter a logarithm with a base and an argument, we call this number the argument, if the base and the argument are the same, then the end result is equal to 1. In our third example, log base a of some argument that is a to the power of r. Again, a and r are going to be some numerical value. Right now they're written as a letter because that numerical value is unknown, but it's not like a variable that's going to be changing within the problem. So these are numerical values, sometimes called a parameter, And we're asking ourselves, what would log base a of a to the power r equal? Well, here again, we're still learning this logarithm notation, so it's unlikely that you can tell me what the result is by looking at the logarithmic expression. So what if we rewrite this as an exponential? Following the loop rule, we have a to the x power must be equal to this target, a to the r power. And if a to the x is equal to a to the r, then it would stand to reason that x is equal to r. Therefore, if x is equal to r, then the logarithm base a of a to the r power is equal to r by itself. And so we can use that definition from before, in green here, to rewrite this exponential as a logarithm if we find it helpful. Now, I'm not entirely certain that it is always going to be helpful, but in this case I think we're going to get away with something here. This exponential's base is a, so I can rewrite this as a logarithm with that same base a. Now, instead of writing a to the power of logarithm base a of m, I'm going to write the logarithm base a with an argument of x, and that equals the logarithm base a of m. Again, if we think of that loop rule, we're starting at the base a, looping across to this argument, which happens to be an entire expression, and a to this power must be equal to x. And that's exactly what we had at the top here. A to that power is equal to x. So we didn't actually solve anything yet. We've just rewritten the problem into a more usable form. At least I would say is a little bit more usable. And perhaps you've noticed this as well. We have a logarithm base a on the left and a logarithm base a on the right. When the logarithms match with bases as well, then their arguments also match or are equivalent. So log base a of x, when that equals log base a of m, then we can make the argument, a true argument, that x is equal to m. So if x is equal to m, then we've got a rule. A to the logarithm base a of m is simply equal to m. And these four rules are simply an exercise in illustrating the rules of logarithms and how we can rewrite them as exponentials. But also they become properties that we may revisit later. We don't always use these rules, but it's good to know that they exist in the event that we're dealing with a large problem and we break it down into smaller components. Some of those components might take the form of one of these rules or properties. In fact, we have an entire list of properties of logarithms that can be referenced in addition to the four that we just established. And rather than go through the process of proving each of these, or at least even anecdotally describing how they work, I'll just talk about them real quickly here and then we'll run into some examples down below. The product property indicates that if we're evaluating a logarithm at the product of two numbers or two expressions, well, we can split apart that product into two separate logarithms. We can split the product that's inside of our argument into the sum of two separate logarithms, and that may be helpful in problem solving. Similarly, if I have a quotient of two numbers or two expressions, then I could split the single logarithm into two distinct logarithms. Those would be separated by a subtraction sign. So our product rule splits into the sum of two logarithms. Our quotient rule splits this into the difference of two log rules. For our power rule, this one's pretty popular. In fact, it's probably going to be the most used property when problem solving. So I'll put up a couple stars around here. This is really a modified rule that's real similar to this last example we walked through. But here we're pointing out that the logarithm of a base, and actually it's pretty similar to the third property as well, but the logarithm with a base a evaluated at m to the r power. If my objective is to solve some sort of exponential problem and I'm looking for this variable here when it's sitting as an exponent, that's a pretty difficult problem to solve because I can't use a square root or any other radical to isolate that exponent. And so what this property is telling us is that we can essentially isolate that exponent. We can bring it down to the front of a logarithm. We could rely on our calculator or our knowledge of logarithms to evaluate this component and then therefore isolate the r value by itself since it's multiplying by that logarithmic expression. So again, in problem solving, we're going to use this technique an awful lot, and generally this technique is used when x, or the unknown variable, is located here in the exponent. And then the very final example here essentially talks about ways that we can change bases or deal with any unknown base a in terms of the natural base e with a natural logarithm. Not very common that we'll use this too much, but I left it in here just in case we need to reference it at another time. So here's our first example for the video. Expand the following logarithm using the properties from above. Now, if I've been told to evaluate this logarithm, that's going to be very difficult to do. But what you might notice is that this logarithm has a product or a series of multiplications that are happening inside this grouping symbol. And if I'm being perfectly honest, a lot of times we'll put that grouping symbol surrounding that argument so that we know that these are all inside of the logarithm's argument. This phrase here is just reminding us that x is positive. We wouldn't necessarily execute this logarithm if x were negative. So the first thing that I'm going to point out here is that this radical, this square root that's capturing x squared plus 1, that can be written as a power because and that's going to be helpful because we have a power rule inside of our list of rules above. So I'm going to rewrite this as x times x squared plus 1 to the 1/2 power. That's a property of exponents that we've learned about in the past. The radical can be rewritten as a rational or fractional exponent. So now what I notice is that I have the product of two terms. We have the product of x and this x squared to the 1/2 power. And the product of two terms inside of the argument can produce a logarithm that's split into two logarithms. Those two logarithms are going to be separated by an addition sign. And you'll notice that the base of the logarithm remains the same for each. So we now have log base 5 of x plus log base 5 of x squared plus 1 to the 1/2 power. And so that was us just using this first product rule. Next, we're going to use this power rule because I do see an exponent here that's hanging out outside of our logarithm. So we'll go ahead and bring that down. This logarithm, base 5 of x, remains unchanged. There's nothing we can do to simplify that any further. But now we know that 1/2 times the logarithm of x squared plus 1 is equivalent to the step prior, and we've now expanded this logarithm. We don't have any rules to expand the sum of two arguments or two values inside of the logarithm's argument, so it's not like we can create a multiplication or anything here. That's a common mistake that I see students perform when they're first learning these log properties, but I do want to stress that this is not able to be expanded any further. This expression would be a good final answer. And we didn't actually solve for x in this problem. We didn't completely solve this expression. In fact, there was no instruction to solve it. We were just simply expanding it. The idea is that we might encounter a process like this in the midst of a larger equation that's being solved. And it might be helpful to deal with two or more separate logarithms rather than one large combined logarithm. So again, we're not solving yet. We're just expanding using some of our properties to practice with. Here's another example. We have a logarithm of a quotient of two items. So immediately I'm going to separate this quotient into a subtraction problem. So I'll say logarithm of x squared minus logarithm of x minus 1 quantity cubed. Now you may be wondering, where's the base value for this logarithm? And this is a perfect opportunity for me to point out that if a logarithm is written without the base, we assume that the base value is 10. A lot of times if we omit numbers, we assume that the numerical value that we omit is 1. For example, if I have x by itself, we can assume that there's a coefficient of 1. We can assume that there's an exponent of 1 surrounding it. But that's not the case with logarithms. With logarithms, the base is assumed to be 10 if we omit it. And that's because logarithms with a base 10 are perhaps the most common logarithms that are being used in many scientific computations. So I'm not going to rewrite it anymore after this step. I do notice that I have a power rule here. The exponent of 2 can be brought down as a coefficient, 2 times logarithm of x. And we have the same thing over here on the right-hand side. We've got 3 acting as an exponent, so we'll write 3 times logarithm of x minus 1. Here again, we don't have a rule or the ability to separate this particular logarithm. We don't have a property that separates the difference of 2 values inside of an argument, so we're going to leave this as it is. And in this third example, I'm going to run out of room, so I'm going to move sideways here. Again, we're being reminded that the x values in this problem are positive. And we do that because the domain of a logarithm must be positive. The input must be positive as well. So the ln notation is our natural logarithm. If you recall that this is just a logarithm with a base of e. So if I would argue that the base of 10 is the most popular logarithm, then the base of e is probably the next most popular, and in some circles it's perhaps even more popular than the base of 10. But the logarithm with the base of e is so important that we use its own notation, ln, to represent that. Now the ln notation behaves exactly the same as logarithms, so we can evaluate and expand this logarithm much the same way. I'm going to start off by utilizing the quotient rule. The natural logarithm of the square root of x squared plus 1 minus the natural logarithm of x cubed times x plus 1 to the 4th power. I could use the power rule on this argument. So we have the natural log of, 1/2 times the natural log of x squared plus 1. Remember, this radical is the same as the power of 1/2. So that 1/2 became a coefficient. We have natural log of x squared plus 1. I have a product rule inside of this logarithm, so I'll split that now. We're subtracting, I should say. I'm going to put a big grouping symbol here. Natural log of x cubed plus the natural log of x plus 1 quantity to the 4th power. I'm using a big grouping symbol here because we should subtract the results of this expansion, and that's going to have to be distributed to both of these terms. So the 1/2 natural log quantity of x squared plus 1 is left. This is untouched. I'll go ahead and distribute this subtraction sign into both components. And I'm also going to apply the exponent rule, or the power rule, for this logarithm. So 3 natural log of x and minus 4 natural log of x plus 1. One more time, we're not solving anything yet. We're just using our log properties to expand the logarithms and break them into smaller pieces. It's possible that we find a solution to one of these smaller pieces and then are able to solve a larger problem. To finish this video, I'm going to ask you to pause it and try to condense these 3 examples. So do the exact opposite of what was just done in the last few examples. Instead of expanding them into separate logarithms, I want to condense these into a single logarithm. Pause the video now and resume playback in a moment to check your work. And here we have it. In each of these cases, we were able to condense the group of logarithms down to a single logarithm. In part A, I used the power rule first to bring this coefficient back inside of the logarithm to a power. And then I noticed that there was a sum of two logarithms that had the same base. This rule only works if the logarithms have the same base. And I recognized that this argument 7 could multiply by this argument 3 to the 4th power. And as it turns out, 7 times 3 to the 4th power is 567. So this original problem is really the same as logarithm base A of 567. In a similar way, we can complete part B. I again use the power rule here, where I bring 2/3 inside the logarithm as an exponent. Now I have the subtraction, or the difference, of two logarithms. When two logarithms with the same base are being subtracted, and I know these have the same base because they're both natural logarithms. When they have the same base, I can now combine them into a quotient. And as it turns out, the quotient of 8 to the 2/3 power over 5 squared minus 1 is equal to 1/6. So we now have a nice simplified solution here, single logarithm. And then lastly, for part C, we've got 4 logarithms that can be condensed into a single logarithm, again, because all have the same base. If any of these logarithms have a separate base, we've got to treat them separately. They're not alike the other logs. Now, it is important to note here that we should be following the order of operations when simplifying this. And even though I've got a whole series of addition and subtraction problems here, the order of operations is very clear in stating that we should work from left to right. So you'll notice that I combined these two logarithms first, then I combined these two logarithms second, then I combined the last logarithm on the far right-hand side. Again, very important to follow the order of operations so that we don't get an errant answer at the end. I think I'm going to go ahead and stop the video here and save the word problems for another video. Thanks for watching. Let me know if you have any questions.